In the previous several lectures, we discussed thermal expansion of solid objects and fluid substances. So recall that we said when a substance is heated or cooled, it expands or contracts according to the following equation. So the change in volume of our solid object or fluid substance is equal to the product of the change in temperature that object experiences multiplied by the initial volume of that object or substance multiplied by the coefficient of thermal volume expansion of that object. Now, this equation works well for solid objects and liquid substances, and that's because solids and liquids are relatively incompressible. So in other words, this equation only works as long as our change in volume is much smaller than the initial volume of our object or substance. Now recall that by definition gases are very much compressible. When you take a gas and you place it into a container, that gas will completely fill that container. And that means gases are capable of very large changes in volume. So as it turns out, this equation only works for gases if the pressure remains constant. If we assume that the change in volume of the gas is very small compared to the initial volume of our gas. So generally, this equation isn't very useful for gases. And that's exactly why we need to develop three equations that will give us a relationship between temperature, pressure, and volume of a gaseous system. So let's begin with the first law known as Boyle's law. So Boyle's law essentially assumes that our temperature is constant. So, it states that as long as our temperature is constant and the pressure isn't too high, the volume of the gas is inversely proportional to the pressure of that gaseous system. And that is given by the following relationship. The product of the pressure and the volume of our gaseous system is equal to a constant. In other words, if we double our pressure, the volume must decrease by that same factor of 2. So if we double the pressure, the volume decreases by a factor of 2, so that when we take the product of the pressure and the volume of our new system, the product is always equal to the same constant. Now, if we want to, we can represent this relationship on the xy plane. So our x-axis is the volume, the y-axis is the pressure, and we see that we get the following curve. So as our pressure increases, the volume decreases. Likewise, as the volume increases, the pressure will decrease according to the following curve. Now, the pressure that we are talking about is the absolute pressure. It's not the gauge pressure. So let's move on to the second law, which is known as Charles' law. So Charles' law makes the assumption that our pressure is constant. So if the pressure is constant and if the pressure isn't too high, the volume of the gaseous system is directly proportional to the temperature. So that relationship is given by the following equation, which states that the division or the ratio of the volume to the temperature of our gaseous system is equal to a constant. So if we double the volume, we must double the temperature so that the ratio remains a constant. Now, if we wanted to, in the same way that we graphed this relationship, we can also graph the following relationship that is shown by the following diagram. So the y-axis is the volume of our gaseous system, and the x-axis is our temperature given in Celsius. Now, if we follow the following slope all the way down to where it touches the x-axis, we will reach something known as the absolute temperature. The absolute temperature is given by the following measure. 273.15 degrees Celsius. So notice that at this temperature, the volume of our gas is 0. And of course, that's impossible because our molecules always have at least some amount of volume. So that means this temperature is unattainable. Now, in the same exact way, we can also plot this on the Kelvin scale. The Kelvin scale, also known as the absolute temperature scale, begins at a value of 0 Kelvin. So 0 Kelvin is absolute 0. Now, 0 Kelvin is equivalent to 273.15 degrees Celsius. And if we wanted to, we can develop a relationship between Kelvin and degrees Celsius. So the temperature given in Kelvin is equal to the temperature given in Celsius plus 273.15 degrees Celsius. So for example, if we want to calculate what 100 degrees Celsius is in Kelvin, we simply plug in 100 degrees Celsius into this equation and we get 373.15 kelvins. Now, finally, let's move on to the final law known as Gay-Lussac's law. So the Gay-Lussac's law essentially states that if our volume is assumed to be constant, the pressure of a gas is directly proportional to the temperature of the gas. So in the same way that we have this relationship, we state that our pressure divided by our temperature is equal to a constant. And that's given by the following graph. So our temperature, which lies along the x-axis, given in Kelvin, and our pressure, which lies along the y-axis, we see that if we increase the pressure, our temperature increases. And likewise, if we increase the temperature, our pressure increases by that same amount. Now, actually, these three laws aren't actually laws. They're more of approximations. And they're not laws because if our pressure is very high and if the temperature is low, then these laws won't work. If the pressure is very high, then that means our gas will go into the liquid state or even the solid state. And if our temperature is low enough, our gases will become liquids and solids. So these laws, Boyle's law, Charles' law, and Gay-Lussac's law, only hold as long as our pressure isn't too high and the temperature isn't too low.